Fellow oxygen breathers, I come to you today with an important message about the next generation of wireless signals and how they may affect our health. Hi, my name is Jesse Gilmer, and I graduated from the University of Arizona with a bachelor's in electrical and computer engineering. Aside from a strong foundation of electromagnetism, my studies included a few classes analyzing the interaction of light, also known as electromagnetic radiation, with matter. So, this next generation of wireless signals means higher frequencies. The frequency of 2.4 gigahertz we're used to by now in the form of 4G, Wi-Fi, and microwave ovens. The frequency of 60 gigahertz is one of the new frequencies coming to the next generation of wireless signals. That's 25 times higher the frequency. Does a higher frequency mean that it's more dangerous? Not necessarily. But the reason I'm concerned about the frequency of 60 gigahertz specifically is because it's almost entirely absorbed by oxygen in the air. In fact, the oxygen molecule is resonant to the frequency of 60 gigahertz. If you Google 60 gigahertz oxygen, the first result as of this moment is from RF Global Net. Signal loss of 60 gigahertz under atmospheric conditions is observed to be 16 decibels per kilometer, which corresponds to a 97.5% loss of power or signal strength across a kilometer. In other words, the oxygen in the air absorbs almost all of this energy of this specific frequency. If this frequency is going to be used in the next generation of wireless signals, surely it's been tested and deemed safe, right? In one study, Japanese researchers exposed human eye cells to 60 gigahertz radiation for 24 hours and found no evidence of damage to the cells when they looked at two indicators: damage of the cell's chromosomes and expression of heat shock proteins. No mention of oxygen. This lengthy report from the IEEE's microwave magazine, titled Safe for Generations to Come, discusses several studies evaluating the effects of direct exposure to many frequencies, including 60 gigahertz, on many different types of tissue and cellular function. Not once are the effects on oxygen mentioned. This review article discusses several studies examining tissue and genotoxicity effects, specifically around 60 gigahertz. It even mentions that oxygen absorption greatly limits the range of 60 gigahertz, but doesn't examine any possibility of biological effect from this energized oxygen. If there is one molecule that should be off limits to microwave excitation, it's oxygen. Doesn't it seem like a really bad idea to be gambling with oxygen? The fact that big tech is pushing to roll out 60 gigahertz wireless technology without appropriate testing on the effects of oxygen absorption in living beings is totally unacceptable. It's our duty to preserve the air we breathe and make sure that oxygen is left alone. The idea of urban environments being saturated with this frequency is frankly disturbing. If this frequency is coming soon to our cities, we need to know, how does this energy absorption affect the oxygen we breathe, and how could that affect our health? To answer those questions, we need to know a few things about both the oxygen molecule as well as the 60 gigahertz signal interacting with it. In its ground state, oxygen has a triplet electron structure, meaning it has two unpaired electrons with the same direction of spin. This electron spin structure makes the oxygen molecule paramagnetic, meaning it aligns to and is weakly attracted by a magnetic field, similar to the needle of a compass. The 60 gigahertz signal, being non-visible light, can either be thought of as an oscillating electromagnetic wave or as a particle with momentum traveling at the speed of light. First, let's treat the signal as a wave and see how it could affect the oxygen molecule that way. In the 1948 paper Microwave Absorption Spectrum of Oxygen out of MIT, researchers describe oxygen's interaction with light. This permanent magnetic moment is the cause of the paramagnetism observed in oxygen, and it also allows the molecule to couple to the magnetic field of an electromagnetic wave. Sounds similar to how electrically polar water molecules couple with light waves of 2.4 gigahertz in a microwave oven, causing them to rotate and heat up whatever leftovers are for lunch today. For those of you that need a refresher on how that works, molecular rotation occurs in materials containing polar molecules having an electric dipole moment, with the consequence that they will align themselves in an electromagnetic field. If the field is oscillating, as it is in an electromagnetic wave, these molecules rotate continuously by aligning to it. This is called dipole rotation. So, electric dipoles can rotate continuously with light. But what about magnetic dipoles? Is it possible that oxygen's magnetic dipole can couple with the magnetic part of an electromagnetic wave in a similar way, causing it to rotate? In a joint study between the National Physical Laboratory of the UK and the Polaroid Corporation, called Magnetic Dipole Rotation Spectrum of Oxygen, researchers explain, in order to have an active pure rotation spectrum, a molecule must have a permanent dipole moment. Oxygen, in its electronic triplet ground state, has an electron spin of 1, and hence has a magnetic dipole. This dipole moment results in relatively intense magnetic dipole transitions being allowed in the microwave absorption region of 54 to 64 gigahertz. Excuse me. So it sounds like oxygen is known to have an active rotation spectrum because of its magnetic dipole in the absorption region of 60 gigahertz. Now, the nature of these magnetic dipole transitions involves quantum phenomena that go over my head. I'll leave a list of topics in the description that seem to play a part in oxygen's absorption behavior, but I don't feel qualified enough to discuss them here. If somebody out there who knows more about quantum mechanics and molecular physics wants to reach out and clarify, that'd be great. What does seem clear from the rest of that quote is that a 60 gigahertz signal is very likely rotating the oxygen molecule by interacting with its magnetic dipole moment. That's if we treat the signal as an electromagnetic wave. What if we treat the signal as a particle or a photon? Well, the reason the oxygen molecule has a magnetic dipole moment is because of the orientation of the spin of its electrons. And an electron's spin can only be affected by an exact amount of energy. What if a 60 gigahertz photon has this exact amount of energy? Well, it looks like it does. A 60 gigahertz photon has 0.248 milli-electron volts of energy. This equation for the energy of an electron spin-orbit interaction gave me 0.242 milli-electron volts. That's a minor 2.5 difference. So if this 60 gigahertz photon is affecting oxygen's electron spin, how does that affect the molecule? In the paper, Line Mixing Effects in the Microwave Spectrum of Oxygen out of MIT, the author describes the rotational transitions that occur around 60 gigahertz and states, the above transitions constitute the spin rotation spectrum of oxygen. Sounds like the electron spin is related to the molecule's rotation. In the paper Absorption of Microwaves by Oxygen out of Harvard, the author states, this magnetic moment interacts with the end-over-end rotation of the oxygen molecule, and he describes the accurate theory at the time as being based on the quantum mechanics of the coupling of electron spin to molecular rotation. So if the 60 gigahertz photon is affecting the electron spin, and the electron spin is coupled to the rotation of the molecule itself, then it sounds like this signal can rotate oxygen molecules. Whether we treat the 60 gigahertz signal as a wave or a particle, we see that it's possible, both ways, that the signal is causing the oxygen molecules in the air to spin. Could spinning of oxygen affect the ability of hemoglobin to absorb oxygen? Well, when we inhale, oxygen diffuses into our bloodstream. 4 oxygen molecules then bind to each molecule of hemoglobin. If magnetism plays any part in the iron atoms' oxygen affinity and binding, then rapidly spinning oxygen molecules could make it harder for oxygen to bind to hemoglobin. Considering that both the oxygen molecule and the charged iron atom inside of hemoglobin are paramagnetic, it seems entirely possible that magnetism plays a role here. In the 2015 paper, Discovery of the Magnetic Behavior of Hemoglobin, a beginning of bioinorganic chemistry, researchers from Caltech and University of Rochester state, current views of iron-oxygen bonding in hemoglobin are mixed. It would seem that reality is more complex than implied by the limiting models proposed by Pauling and Weiss. Indeed, our understanding of the iron-oxygen interaction in oxygenated hemoglobin continues to evolve. Magnetoelectrochemistry and magnetobiology are relatively new fields. We're just beginning to understand how magnetic interactions at the molecular level affect the biochemical processes of the human body. From my research, it seems the oxygen molecules are being rotated by the 60 gigahertz signal, and because 60 gigahertz means 60 billion times per second, these oxygen molecules could be spinning pretty quickly, and that could very possibly hinder the ability of oxygen to bind to hemoglobin. This effect on oxygen isn't something we can see, and the research regarding this issue only goes so far. We should only be rolling out this signal if we're entirely sure that it's safe. The idea that big tech will soon be experimenting with our air is frightening, especially when there haven't been studies analyzing the effect on oxygen absorption in living beings. Ultimately, we don't know how this signal will affect our ability to absorb oxygen. Until we get to the bottom of this, we must stop the rollout of this technology immediately. Together, let's preserve our air and make sure they leave oxygen alone. Alrighty, y'all, thanks for watching. If YouTube misplaces this video, you can find it at leaveoxygenalone.com. Please share this message so that together we can get to the bottom of this. Thank you.